riveting, joining two sheets of metal with red-hot rivets to make a ship. Using a hammer or a compressed air rivet gun, it is the absolute image of manual labour, men making things. But it's shipbuilding's relationship with machines that changed industry forever.
Engineering components like these aircraft parts takes precision, a precision that can only be achieved with a machine like this. A state-of-the-art machine tool.
Look at that. Very satisfying object indeed. Beautifully engineered. It's an impeller from the Eurofighter. Not sure I should have told you that. Anyway, it's made on a machine like this, and it's capable of working to tolerances of 2 to 3 microns. That's 2 to 3 millionths of a metre. But the idea that you could make something this complex not by hand on a machine accurately and repeatedly started 200 years ago.
Machine tools were the unsung heroes of the Industrial Revolution. Without them, the spectacular feats of 19th century engineering would not have been possible. And it all started with a naval problem and wooden warships.
HMS Victory, Nelson's flagship at the Battle of Trafalgar. Built in 1756 from 50 acres of woodland.
Every single piece of wood in Victory was cut and shaped by hand. And at the start of the 19th century, as war raged between Britain and Napoleonic France, it was only wooden warships like her that kept us from speaking French. But building and repairing these ships by hand was becoming a major problem for the Navy. Take one apparently simple but crucial component: blocks for the rigging. Ships like Victory needed over 1,000 of them.
Nobody knows who invented blocks. The Greeks had them. The Vikings had them. It's like trying to find out who invented the wheel. It has a sheave, a roller, and a rope is rove threaded through. This block has 2 sheaves, and so does that one up there. This means that you have a 4-to-1 advantage. The rope passes 4 times through the sheaves. So any weight on the end of here takes 4 times less power to lift.
Accurately making these complex parts by hand was difficult enough. But in the heat of the Napoleonic War, when Britain faced invasion, the blockmakers just couldn't cope with demand. But then, Marc Brunel, a young French refugee, arrived at Portsmouth with a solution: mechanisation.
The Admiralty went to the brilliant young engineer Henry Maudsley for the machines to Brunel's designs. Machines for cutting, mortising, boring, shaping, corner cutting and scoring. So that, by 1805, the Royal Navy was supplied by the world's first steam-powered block-making factory. And this is one of the original machines, a 200-year-old machine tool. This saw blade rotates like that. You can see the belt drive here, which would have been from a central takeoff from the steam engine. This cleverly here, there's an additional element to this machine. We can now start to see these brilliant engineers applying their minds to the problems of repetitive production of accurate components, because this contra-rotates the other way, against the saw blade, ensuring a very, very accurate cut.
The block mills were the first place in the world where machine tools, not hand tools, were used to turn out a product accurately, and they were doing it in huge numbers. At their height, the mills produced 130,000 blocks a year. They're all rather ghostly now, but it would have been a place full of noise and wood shavings.
A lot like this, in fact. How good is that? This is Stotts Park Bobbin Mill. It's basically a wood-turning mill. You start off with wood, and you end up with these bobbins, simple turned wooden shapes with holes through the middle. Used to winding things round, thread, sewing thread, even wire.
toggles for Royal Naval duffel coats. This place demonstrates exactly Brunel's block-making system, but here at Stockport Bobbin Mill, it's all still working.
This may not be as complicated as block making, but it shows how a job traditionally done with hand tools could now be done with a series of machine tools.
Power to the mill was provided by a steam engine. This single cylinder, built by Bradley's of Brighouse in Yorkshire, driving a wheel which drives a belt to take the shaft driving throughout the factory to drive the individual belts to drive every single machine.
The mill also depended on a regular timber supply, and much thought went into managing its impact on the surrounding environment.
This mill was surrounded by trees, but they're all still here because they didn't just chop them down, they were carefully nurtured via a system called coppicing. Ash and birch were cut off at the stumps and encouraged new growth in poles between 7 and 20 foot in length, and these were cut on here and then taken to the next process.
The first machine was for boring a hole through the middle of each cylinder of wood. Then this machine roughed out the wood cylinder, cutting down the ends and shaping the middle. Now it's starting to look like a bobbin.
This finishing lathe uses two sets of opposed tools to put a bevel on the bobbin and to finish the edge, like this.
If you know how to use it, that is. But once you get the hang of it, you can turn out bobbins in their thousands. Now just one step remains.
And finally, ladies and gentlemen, we come to the tombola. Of course, it's not a tombola, it's a polishing barrel. The bobbins will be put in with beeswax. This one's not collected to the line drive by a belt, but that's where it would have been. And then the bobbins are polished so they're smooth and don't snag the threads. Bobbins by the hundredweight.
Stott Park Mill made bobbins for the lucrative cotton industry in nearby Lancashire. The machine tool technology, pioneered in the block mills, had been put to a commercial use. But as the 19th century wore on, it was still naval shipbuilding that led the way in engineering.
Reluctantly, the Royal Navy realised the age of wooden shipbuilding was over. To keep ahead, they needed to build iron ships, and that created a whole new set of problems for engineers.
This is HMS Warrior, the Royal Navy's first iron warship. Launched in 1860, she could outgun and outrun every ship in the world. These two huge steam engines gave her a top speed of 15 knots. Flat out, they would have turned at 56 RPM, and the strain of working under such conditions demanded each part fit together perfectly. A daunting challenge for the naval engineers. Building the hull in itself was a feat.
Here, on the gun deck of HMS Warrior, we can see her construction. The riveted iron hull, protected by a band of teak 8 inches thick, running horizontally. A further 10 inches laid vertically on top of that. And then here is the armour plating. This was designed to withstand any shocks from the new explosive shells that had replaced round shot. Each piece of armour plating is 15 feet by 6 and weighs 4 tons. And if you think they're impressive, what about the machines that made them?
The steam hammer, invented by James Naismith in 1838 to forge a crankshaft for the ship Great Britain. Forging parts for ships required far more power than any blacksmith could muster. You beat the iron to make it stronger, and steam hammers could beat and strengthen really large bits of iron, ready to be shaped by rollers. And giant rollers needed a giant power source.
If you build warships like Warrior, you need big tools and big machines. As the Brummies say, you need a big hammer to knock in a big nail. And this
is a big honour. It's not a hammer, of course. It's the River Don engine. It's a 3-cylinder, 12,000 horsepower engine that was used to drive an armour plate rolling mill to build warships like Warrior, and it's my favourite. And if you think it looks impressive now, wait till you see it running. Not only is this engine the most amazing example of the power of steam, the brute force, it's also one of the most agile and nimble machines you'd ever likely to see. It reverses incredibly quickly so that the armour plate can be passed under the rollers and reversed back again, like that.
Jaw-dropping power was one thing, but far more important for 19th century engineering tools was precision.
Now that is a big machine.
In the 19th century, shipbuilding was at the forefront of a new era in precision engineering. The machine tools developed combined power and accuracy as never before.
Power is very important in shipbuilding. Obviously, you have large components. They're large items, ships. But accuracy is far more important. Look, ship's models. Except that these are very important scale models. These are not made by somebody in a shed as a way of getting away from the wife. No offence. It is used by shipbuilders to mark out each individual plate that makes up the hull. Of course, on a drawing, it's almost impossible to show the shape, the curvature of the hull.
Each plate had to be accurately cut and curved to make the hull. And not all metal shaping machines were sophisticated enough to do this.
If you want to give shape to metal, you have to hit it. Metal bashing, it's called. You can hammer it with a steam hammer, you can roll it, you can press it, or you can punch it. Here, we're making a shovel. So the die looks exactly like a shovel. You put a piece of metal in that when stamped will conform to your pressed shape, and you wallop it.
But here at the Summerlee Heritage Park in Coatbridge, there are far more sophisticated tools for far more complex jobs.
A radial drill, lots of possibilities for movement along that axis, and also you can move the drill head like that, and then if I put this into gear, the bit will start to turn. Lots of strength in this machine, lots of stability, very accurate.
Machine tools made a revolution in heavy engineering possible. Constructing railway locomotives and steamships demanded work at fine tolerances on a large scale. Take a classic example, the lathe.
On a drill, the bit moves and the job stays still. On a lathe, the job moves and the bit stays still. As it revolves, you address the tool to the job. You move it along the face of it. That's what you're working on with this capstan. Then you can move much more slowly. There's a 10-to-1 reduction here. We can move at 1/10 the speed. So you can work very accurately along the face. Of course, in shipbuilding, component parts like the propeller shaft, which link the engines to the propeller, funnily enough, are very long pieces of metal. So on a lathe like this, you can cut very accurately over a huge length, like this.
Machine tools can do the same job again and again and again. And once you're turning out component parts in large numbers, then another issue comes into play: standardisation.
Take screw threads, for example. Before standardisation, if you needed a screw or screw thread for a fixing, you'd cut it by hand with a file to fit the particular job you wanted. But
With bigger and bigger machines and more complex machinery, that old style of individualistic hand-to-eye workshop engineering wouldn't do anymore. So, to avoid chaos and a lot of screwing around, screw thread sizes were standardised by a man called Joseph Whitworth. Whitworth was an apprentice of Henry Maudslay, the groundbreaking engineer who'd built the block-making machines to Mark Brunel's designs.
What Whitworth realised was that if you standardised the cut, you wouldn't need to do it next to the job. You wouldn't need to keep making sure it was a good fit. You could standardise it. Therefore, you could make them anywhere, and the screws would always fit. After looking at thousands and thousands of screws, lucky man, he decided that the very best fastening was achieved when you set the threads exactly 55 degrees apart and then rounded the tops and bottoms at a radius of 0.1373 times the pitch. So there. He then set about producing screw-making kits. J. Whitworth and Company, Manchester. And he was so successful that by 1860, his measurements were standard across the whole of the British Empire.
Now, with screw-cutting lathes like this, working to Whitworth standards, you could turn out screws in real volume. Manufacturers could just buy them in and be sure they'd fit into the relevant holes. And this same principle could be applied to all sorts of components across all aspects of engineering. These highly developed machines, whose sole purpose was to make other machines, helped British industry become the best in the world, and shipbuilding was no exception.
By the late 19th century, Britain was turning out 1 million tonnes of shipping a year and rising. And this building is an expression of that period of huge confidence and ability. Built by Alexander Stevens and Company. It was their engine shop at Linthouse. It's enormous. Built by men in top hats who had no doubt that what they were making was the best in the world. Clyde-built ships. Believe it or not, it's not on the banks of the Clyde anymore. It was moved 30 miles to Irvine and is now the centrepiece of the Scottish Maritime Museum. And it looks every inch the part, in my humble opinion.
British engineering may have led the world in the 19th century, but in the 20th, it saw a steady decline. In 1900, there were around 50 shipyards in Scotland alone. Now they've almost entirely disappeared.
This is Ferguson Shipyard, the last commercial shipbuilders on the Clyde. And that is a ship, a 2,200-tonne ship, and it's about to be launched. And do you know what? There's nowhere else in the world I'd rather be.
And here in Ferguson's fabrication shop, you can find today's shipbuilding tools, the great-great-great-grandsons of the block-making machines.
Iron and then steel plates for hulls were always cut on the pattern loft, laid out, marked out and cut by hand. Now they're laid on a machine and cut by computer.
This is a plasma steel cutter.
This is an incredibly accurate machine. It uses nitrogen, oxygen, a spark and air to liquefy the metal. Please, Tommy. And it can cut 40 metres an hour.
The cutter works to pinpoint accuracy within 1/10 of a millimetre.
You need to cut a shape, you need to use a torch or a cutting machine. However, if you just want to cut a bit off, you can use brute force. You can use a guillotine like this. Bit of French chalk across there. You line up your chalk line and then you cut. Perfect. Once you've cut your metal, you need to shape it so it conforms to the hull, the ship's skin. Shipbuilders call it the shell, and these are shell rollers. Back in the day, the job used to be done by hand, by hammer, but
rollers, obviously much more efficient, and as time went on, they got bigger and bigger. These are some rollers, they're quite large. Pressures put on the work by these rams. One there, and the other one 18 metres away. And the pressure that this machine can bring to bear on the shell rollers is 1,000 tonnes, ladies and gentlemen.
With all that huge power, these giant rollers can give graceful shape to thick sheets of steel.
You can see how the shipbuilders and riveters on this Clyde puffer have adapted to the stern of this boat right round the prop shaft housing here. It's almost like they've put a skin on it. Nice. I'd like that one, please. I'll have that one, thanks.
And when you've finished building it, hopefully it's watertight, you've got to launch it.
See that water? That's the Clyde. See that? Steel? That's a ship. All that's going in there. This is the FPV Jura, a Scottish fishery protection vessel, and quite possibly the last commercially built ship launched on the Clyde. The system works like this. There's a standing way, this one stays still, and a sliding way. That's the medium we use, grease. Then the whole lot goes stern first into the Clyde. And that might be the last time.
There's a strange mood in the air. The ship's launch should be about celebrating the culmination of much hard work and skill, but it's tarnished by worries about the future. This vessel's sister ships may be built in Poland, where it's cheaper. Ferguson's is already struggling, and losing that work would be a nail in the coffin. The men here know their jobs hang by a thread.
Count these men's heads and count the years of apprenticeship.
So this could be one of the last times a ship is ever launched on the Clyde. When you think about its proud history of engineering innovation, it's very sad to think that British shipbuilding has come to this.
3 cheers for Europe.